And now I give you Segev Wasserkrug from IBM Research in Haifa, Israel.
Okay, so thank you. Good morning. Before I begin, I want to say it's an honor to be here, and I'd like to thank the judges for giving us the opportunity to present in the prestigious, in the finals of the prestigious Daniel H. Wagner Award. So I'm here to present the work Optimizing Water Distribution Pressure Management at Valley of the Moon Water District. My co-authors in this work are Alexei Tsitkin and Sasha Zadorojny, also from IBM Research. So my presentation is composed of three main parts. In the first, I'll give an overview of the pressure management in general, and then talk about the particulars of the water utility with whom we've worked, Valley of the Moon Water Districts. I'll then go into a little detail about the solution, focusing mostly on the optimization algorithm that we used. And the final section will be how we actually applied the results, the actual physical networks, the results obtained, and I will close with a summary of the presentation. So the broader context of the work is operational management of water distribution networks. And in this context, it turns out that pressure management can significantly help with two major operational issues. The first is water loss. This is an operational issue that plagues many water utilities worldwide and is a major issue, not just in terms of costs, as can be seen, approximate about $14 billion, but also in terms of the actual amount of water lost. And the second is energy, just looking both from a perspective of the national amount of energy required to provide or treat water, but also from the perspective of the individual water utility. As can be seen, this is one of the major operational costs of most water utilities. So how can pressure management help with these two aspects? The first, in terms of water loss, due to the relation between pressure and flow, reducing the amount of pressure by 10% on average reduces the amount of water loss by an equivalent percentage. And in terms of number of leaks and bursts caused, it turns out the relationship is even greater. Approximately reducing by 10% causes 14% reduction in new leaks and bursts. In terms of energy, obviously reducing the amount, I apologize for this. Reducing the amount of water that needs to be distributed reduces the amount of energy required, but in addition, many water utilities need pumping in order to provide the required pressure. So the ability to reduce the pressure automatically leads to a reduction in pumping. So obviously, pressure management can bring significant benefits. However, there are many challenges water utilities encounter when trying to implement efficient pressure management. The first is that pressure management can be influenced by a variety of equipment, pumps, valves, tanks, and so on. So it's very difficult to find the right balance, how to control or manage each piece of equipment individually while taking the entire network into account. The second is that there may be many conflicting goals or several conflicting goals when trying to manage pressure. While I mentioned two strong reasons for trying to reduce pressure previously, there are also reasons for trying to increase pressure, for example, to maintain tank water level in case of emergency. Obviously, also, sufficient pressure must be provided to provide adequate level of service. The third issue is the issue of visibility. Many water utilities don't even know what's going on in the network in terms of pressure. While it's very easy for any experienced water operator to define what are the pressure critical points, which are the points in the network that give a good view of the pressure, many water utilities don't have these control points or these points monitored, so they don't even know what the actual pressure is. And the final issue is that while it's fairly easy to maintain a constant pressure at the input to the network, at the valve or at the control point, this actually leads to a very varying pressure at the pressure critical point due to the fluctuations in demand. So on the one hand, you have a very pressure management can lead to significant benefits. On the other hand, there are several challenges associated with managing it effectively. So it seems like a very natural place to try and apply analytics and optimization to bring the benefits. However, it turns out there are several challenges with applying analytics optimization to this field. The first challenge is that a lot of the data upon which decisions need to be made come from physical sensors, which are limited in accuracy and very often faulty, produce erroneous data. The second is that what we are trying to control is an actual physical system, a physical network, and so we need to model to bridge the gap between the mathematical models that are used and the actual physical system. And finally, whatever tools that we create ultimately need to be used by the water operators, by the people managing the network. There are people much more experienced to hands-on management of the physical equipment and less used to advanced decision support system. And all of these issues we had also to deal with when working with Valley of the Moon on this project. So Valley of the Moon is a water utility in Sonoma County, California, responsible for managing approximately 92 miles of pipe, providing water to about 23,000 customers, most of which are residential, some are commercial. The majority of the water is provided by an external source, the Sonoma County Water Agency, with the remaining 20% being provided by wells within the network. And they have an estimated 8.5% water loss. Through this project, we worked very closely both with Valley of the Moon Water District and with the Sonoma County Water Agency, which are the external provider of the majority of the water. So what was the status of pressure management before our work began in Valley of the Moon? So overall pressure in the network is controlled by 12 pressure-reducing valves. However, the majority of the network is in one pressure zone controlled by 10 valves, such that each valve can potentially impact the entire system. The remaining pressure zones are on the mountains on the other side of the valley, with the main pressure zone being in the valley between the mountains. And the main issue, as described by Valley of the Moon when we began our work, is the issue that we're experiencing in the seasonal transitions, either from winter to summer or summer to winter. To give a specific example, as summer turned to winter, the demand dropped, resulting in an increase in pressure, which led to these pressure spikes which appeared here, and as a result, a large number of leaks and bursts occurring during those seasonal transitions. Previously to our work, the way the pressure management status in Valley of the Moon was that, first of all, they had a significant data gap, which had two aspects. The first aspect was the fact that they did not even have all of the pressure points monitored. So they did not even know what the status was in terms of actual pressure in the network. The second is that some of the data which was available, they received very infrequently. For example, data, Sonoma County Water Agency had daily data on how much water was flowing into the network, but Valley of the Moon only received it every month. So they did not have a good picture of what was going on. Based on the complexity of managing those 10 valves simultaneously and also on the data gap, the way they managed pressure was a very active manner. Waited for issues to occur, such as the pressure spikes that I showed previously. Then, based on the month-old billing information, decided which valve to change, made a small change to the valve, and repeated the process as necessary. An important point to mention is the actual changing of the setting of the valve is a very physical process, which I will now show. So these are the pressure gauges used to actually check what the settings are. As you can see, this is the head of operations of Valley of the Moon, going down into the vault where the valve is and using a wrench to make the actual physical change, checking every now and again what the settings are in terms whether the change has the desired effect on the gauges. And now this physical process is something we had to stay with, the actual changing of the valve, the physical process, because they did not want to invest in bringing electricity to those valves so they could be remotely controlled as part of the project. So this gives a background. Now let me talk about the system itself. One of the major issues we had to deal with is a non-convex optimization problem resulting from the need to model a actual physical system. Now, our primary decision variables in the problem were the actual settings of the valves. However, these settings had an impact on the pressures and flows throughout the network. So these also became decision variables in our we had to take the entire network into account when deciding or when optimizing the settings of the valves. And one of the ways in which the network had to be taken into account is to adhere to the physical laws governing the flow of water in the network, one of which is energy conservation, for which the equation appears here. So this describes the flow of energy going from point D1 to point D2. And so the pressure or energy loss between these 2 points is equal to the flow raised to some power times a constant. And so the variables in this equation are the 2 flows, the PD1 and PD2, and the 2 pressures, PD1 and PD2, and the flow going across the network. As you can see, this is a non-affine equality constraint, which results in a non-convex formulation. Another thing that's important to note about this equation is that the direction of flow is assumed to be positive, because the flow because flow causes an energy loss, it can always needs to go from a high energy to a low energy. Now, this obviously can be modeled using integer variables. However, this compounds the computational issues associated with this problem. And a final point that needs to be taken into account is that the valves themselves, their behavior is discontinuous, because they can shut off and then close the water flow at a particular time. And this discontinuous behavior also needed to be modeled in value of the Moon's network. So how did previous works attempt to optimize water distribution network? So the first line actually is not a previous work, but it's a tool that's very common in the area of water distribution network, which is called the hydraulic simulator. This actually does not have any optimization capabilities, but given a specific settings of the equipment, the pipes, the valves, and so on, this can very efficiently compute the flows and the pressure throughout the network. So based on this one possible approach, which was tried by many, is using meta-heuristics, using this as a black box to search for the optimal solution. Another approach is to use to very explicitly model the nonlinearities using techniques such as mixed integer nonlinear programming. Now, both these approaches suffer from 2 main issues. One is that there are no theoretical optimality guarantees, and the other is that is of computational issues due to the need to run multiple iterations in the first case, or due to the algorithms available in the second case. Another approach, which is somewhat closer to the approach that we took, is linearizing or relaxing the nonlinear problem, and then using techniques such as branch and bound in order to then find the actual optimal in the actual optimization space. And none of these works address the explicit modeling of the valve, which I mentioned, added to the computational issues. The approach we took is a linearization approach, and it was based on the following 2 key observations. The first is that for the specific values of the constants available in the water networks, the relatively large differences in flow cause both absolute and relative large reductions in pressure, which means that, say, if we are to take the first order Taylor approximation around the flow of 200 gallons per minute, reducing or increasing the flow by 100%, as can be seen here, you get very close results to the linear approximation and to the actual energy loss, both in terms of relative and absolute values. Another observation is that for many parts of the network which have a single path leading to them, their flow is completely determined by the demand, because no matter what the pressure is, there's only one path the water can take, and due to energy conservation, due to mass conservation, which is another constraint, this path must be followed. So, based on these 2 observations, our approach said, okay, let's try to linearize the problem. And so if we were given assume we are given a good approximation of the actual flow of the optimal solution, then we could use the first order Taylor approximation, which immediately translates the equation that appears here. Now, this still assumes the directionality of the flow. However, in order to overcome the issue of directionality, what can be done is that the original constraint can be reformulated as specified here. And then in this constraint, the flow is now no longer assumed to be positive, but the first order Taylor approximation can still be taken and linearized. So then the question becomes, how do we get a good approximation of the flow around those points so that we can get a good first-order Taylor approximation. So what we utilize is the fact that we're optimizing an existing network in which there are settings already in place. So we took the current network setting and using the tool, the hydraulic simulator tool, which I mentioned previously, very quickly calculated the pressure and flows at the current status in the model, used the flows as the basis to do the first-order Taylor approximation, solve the problem using mixed integer linear programming. The need for mixed integer arose from the discontinuous behavior of the valves, but now as there are only 10 valves, the number of integer variables is significantly reduced. And then we add an additional step of using a local search heuristic around the solution provided by the linearized approach in order to improve the solution, and this is the solution that we output. So basically, at a high level, this can be considered as a heuristic which attempts to find an optimal solution in approximated space and then tries to improve the solution in the actual optimization space using a local search algorithm, and also ensuring that the solution adheres to the actual constraints in the approved optimization, in the actual optimization space. So we did some theoretical, empirical examination of our algorithm. One of the things that we compared it, we did some comparison with a nonlinear programming, direct nonlinear programming implementation, which did not have explicit modeling of the valve, so no integer variables whatsoever. And the results appear here for various networks. What can be seen is that for our network, for value of the moon, it's almost 6 times the performance difference. In all cases, the performance in terms of objective function was almost equivalent. In most cases, our algorithm was better. This last line is empty here because when trying to model 24 hours, the nonlinear approach was not able to find a feasible solution due to the fact that it did not have the integer variables, the discontinuous behavior of the valves model. It could not even provide a feasible solution. Now, another use for the nonlinear programming is that we could use it to find or to get an idea of how far our solution was from the optimal, from the theoretical optimal. So when we did this by using SDP relaxations for the nonlinear model, in all cases, the nonlinear model that we tested, we could not test them for all networks, but for some networks we could test them. For all networks that we could test them, the result was less than 7% and significantly smaller for most of the networks. Now, and due to the closeness of the results between our algorithm and nonlinear, this also gives us a good or some idea of the bound between the theoretical optimum and the results achieved by our algorithm. Now, obviously, this optimization, which I focused on in this presentation, was only part of the solution, an important part, but a part nonetheless. In order to come up with a useful tool, we had to create a comprehensive operational solution that could be used by the water operator, that was intuitive and so on. Now, this and a picture of the user interface of this tool appears here. Now, this not only provides detailed recommendations, which is the part that appear at the bottom here, which says for each valve what should be the setting, but also gives a very comprehensive view of the entire pressure status of the network. In order to achieve this comprehensive view, as part of the project, additional sensors were installed at those pressure points which were previously not monitored, and we ensured that the available relevant information, such as billing, was provided to this tool and consolidated in a much more frequent basis. Now, this solution, then, this overall solution not only incorporated our optimization algorithm, but had additional novelties, such as an objective function that was both tailored to the water operator, and very intuitive for the operator to specify and to indicate that different pressures needed to be maintained in different parts of the network. Another thing we need to take into account is robustness. Due to the fact that the changes to the valves could only be carried out manually, the frequency at which the changes could be carried out was once every several days at the most, with the preferred frequency being once every 2 weeks or something like that. So the robustness to the changes in demand between settings had to be taken into account, and we did this by And we explicitly did this by incorporating a scenario-based approach, the details of which appear in the article. Two other aspects is we needed to, while we had a pretty good model of the network in terms of hydraulics, there were still some gaps, so we needed to have a methodology to bridge this gap. We came up with a methodology to bridge the gap between the numbers produced by the model and the actual pressure management in the network. And finally, another thing to add as part of this work is the framework for the automated generation of optimization formulations from network description, so that we could, if the network changed, we could adapt to it, and we could also accommodate or take into account additional networks or additional needs such as pump optimization. So now that we have the solution, let me tell you about how we actually applied it out in the field. So we began our work in June of 2011, and our first goal, because the near seasonal transition was from summer to winter in October, our first goal was to try and capture this transition, right, to try and reap the benefits as soon as possible. So first, using the consolidated data now, we could decide up front, together with the value of the moon operators, when would be the good time to make the change. This is the first time that the decisions were made up front, not waiting for issues to occur. So when we saw these demand changes and these pressure increases, these gave us a good indication of when to make the change, and we scheduled the change for the last week in October. It's very interesting. I came to Valley of the Moon on Sunday before the planned changes were going to be made, ready with a set of changes, pre-analyzed, tested in the lab setting and so on. Coming to the office Monday morning, and then the chief of operations can say, look, we've had now a major issue. One of the wells is malfunctioning, no longer providing water. Now, and one of the tank levels now is dropping dangerously, which may result to an issue of being able to provide water to one of the pressure zones on the mountains. So can your tool help me with this? That is, can your tool help me increase the pressure in that part of the network without impacting or trying to maintain the rest of the network? Now, what we found is that thanks to our objective function formulation, it was fairly easy to accommodate this request for a change. But now the priorities changed. Now the main priority was to increase the pressure in that part of the network, and the secondary priority was to try and maintain or lower pressure in the other parts of the network, but much lower priority. So we analyzed the change, did some runs, then came the next day with a set of changes, did some initial analysis together with the head of operations of Valley of the Moon, and went out and made changes to 4 valves. This can be seen in the picture here. This is the first time that more than one valve was changed simultaneously by Valley of the Moon. And the results can be seen here, that after we made this change, this indeed resulted in the dramatic increase in the water level in the tank. And now after this change, encouraged by the results, then we went out and tried to then lower additionally the pressure in other parts of the network to get a more balanced pressure status overall. So this was the first time we used the tool. We and Valley of the Moon considered it a success. Based on this success, since then this has now become the tool they are always using to make any pressure settings changes in the network. Another interesting phenomenon that we've observed, they now have the confidence to make the changes much more frequently than in the past. Whereas in the past they tried to limit to seasonal changes, now they are happy to make it once every week or once every couple of weeks, obviously resulting in much better pressure management. And another interesting point is since October of 2012, they've actually been using the tool completely by themselves, which means that we've succeeded in another of our objectives, which is providing a tool that is suitable for the water operators. They don't need our assistance to come and hold the tool. And these are 2 quotes provided by Paul Gradolf, the head of operations. This is the gentleman we saw at the beginning of the presentation climbing down to the shaft. And one of the things I like about these quotes is that me and I guess many other people have tried to apply operations research to any domain, come to the domain expert or the person working in the domain, and many times get the reaction, I'm an expert, I've been working in this field for 30 years, and no way an automated system or some mathematics is going to be able to do a better job than what I can, given all my experience and knowledge and so on. And these quotes say exactly the opposite in some sense. So these are in terms of the usage of the system, but now in terms of results. So as I mentioned, our primary objective was to reduce the number of leaks and bursts in seasonal transitions, but we obviously didn't want to impact the leaks and bursts throughout the year. So what we did, in order to ensure that we had reliable results, we measured for an entire year since the first implementation from October 2011, the number of leaks and bursts, and what we observed is a 16% reduction in leaks as compared to the previous years, or 19% compared to the previous 3-year average. Our value of the moon estimated that if this were to translate to an equivalent reduction in water loss, this would almost reduce 2% in their operating expenditure. Now, for value of the moon, this is $60,000 per year, but to give a context, their water utility whose overall annual expenditure is on the order of $5 million, including operation and any other costs. And obviously for large utilities, this could be significantly greater. Just to give a specific example, for one of the utilities we've had some discussions with, they estimate that 1% of water loss is equivalent to almost $3 million of costs per year. So given their level of water loss, a 19% reduction translates to almost $4.2 million of savings per year. Now, another important point is that this not only saves due to reduction in water loss, but it also saves in pipe repairs due to the need to fix less bursts. And this $4.2 million doesn't take those repairs into account. This is just in terms of the water loss. And this is the quote provided by the general manager at the time, Krishna Kumar. Additional results we've obtained is potential savings due to property damage caused by large bursts. And Valley of the Moon personnel told us that just one such burst in August caused almost $20,000 worth of damage alone. Savings due to reduction in water loss from existing leaks is not something that was measured, but this is also something that all the literature says that better pressure management leads to. And things such as reduction in pressure spikes, improved tank levels, as I mentioned previously, which is just one example of improved customer service in terms of pressure, and improvement of water exchange in tanks, which reduces the number of quality issues due to stagnation of water. And this is another picture, which is before and after, the classical before and after picture. Right, so this is the before, the pressure spikes that I showed in the beginning. And this is the same month after, in the year after we began implementing our solution. You can see a much smoother pressure line here. I'd like to close this section with a brief message from Krishna Kumar, who was the general manager of Valley of the Moon at the time of the project.
Hi, my name is Krishna Kumar. I am the general manager at Marine Municipal Water District. Previously, I was the general manager at Valley of the Moon Water District in Sonoma, California. In that capacity, I had the opportunity to work with a team of IBM professionals in developing and implementing a pressure management solution. Valley of the Moon Water District has a very complex water network which requires the simultaneous use of up to 10 valves. The objective is to reduce the number of leaks and bursts during seasonal transitions, and also to maintain tank levels and making available required fire flow. With the implementation of the IBM solution, we were able to move from a very reactive approach to a very proactive approach. The implementation resulted in dramatic reduction in the number of leaks and bursts that we experienced. There was actually a reduction of up to 19% in the leaks and bursts, which obviously meant operational cost savings as well as improved customer service. I'm pleased that Valley of the Moon Water District customers continue to reap the benefits of the solution. I also wish IBM the very best in getting this effective solution to other water utilities across the globe. Thank you.
So to summarize my presentation, we consider this a very successful application at Valley of the Moon Water District, not only in terms of the actual quantitative and qualitative results achieved, but also in terms of both customer satisfaction and appreciation gained by people in this field to the capabilities of analytics and optimization. As I mentioned previously, we had to create an end-to-end solution which included several novelties, including optimization algorithm, that also incorporated the robustness into account, a specialized problem formulation, and a usage methodology to overcome the gap between the actual network and the model, and the mathematical model, and incorporating all of this into an end-to-end solution that had many other technical challenges, including data integration, cleansing, and so on, and presenting this and incorporating all of this and providing it to the user in a consumable manner. Moving forward, what we've ended up with a framework is a fairly generic solution that we believe is applicable to many water utilities worldwide, to provide them benefits such as reduction in water loss and repair costs, depending on the specific utility, also additional benefits such as a reduction in energy costs due to pumping. The benefits in terms of monetary benefits could be significantly greater, as the example I showed previously. And for large metropolitan areas, another effect that needs to be taken into account, another benefit, is the potential reduction in births in heavy metropolitan areas, which result in significant city disruptions or city pulse disruptions. And we have ongoing discussions with several cities around the world, and we hope to provide them the additional utilities with not only operational efficiency, but also help them to conserve these precious natural resources. So thank you.